missed my lunch.
Hi, everybody. Welcome to Read Science. This is Joanne, or Science Goddess on Twitter, and I'm joined today, of course, by my co-host, Jeff Schomeyer. And our guest today is Graham Farmelo, who is author of a couple of my, well, one of my favorite books, and then a brand new book, I should say, which I enjoyed. So this one, The Strangest Man, I'm only bringing this up. This isn't the new one. What, this 2009?
Yep.
So anyway, I love this book. It kept me, the audio version kept me company on a long car ride, but fantastic. Well received, wasn't it?
Oh, yeah, thankfully, yeah.
And then we're going to be talking a bit today about his new book called The Universe Speaks in Numbers, How Modern Math Reveals Nature's Deepest Secrets, with a lovely cover. And yeah, so why don't you say hi to our guests, Graham?
Hi, it's really nice to be with you. It's been an ambition of mine to be on your show, so I'm delighted to be with you.
Great, thank you so much.
That's a very nice compliment, but it's been an ambition of Joanne's to find an excuse to talk to you ever since she read the Dirac book.
Well,
yeah,
this
that's
sounds
true.
like it sounds like a mutual admiration society.
That's right, because we weren't quite doing this show back then.
Yeah, no, I know. Anyway,
we had to wait for technology to make this happen. So anyway, so I'm going to read just this brief bio from Graham's website, which actually is pretty snazzy. Anyway, it says here, you are a biographer, science writer, and commentator, but so much more. Formerly an academic, museum professional, and undercover restaurant critic, Graham is an award-winning biographer and science writer. Based in London, he is a fellow at Churchill College, Cambridge, and a regular visitor at the Institute for Advanced Study, Princeton.
Which is where I am now.
Yeah, that's where you're sitting now. So hopefully the weather's nice. As interested in the arts as he is in science, he is a keen consumer of theater, exhibitions, music, film, podcasts, and above all, books. Oh, we love to hear that.
Good. You got it. That's a pretty good summary.
Yeah, well, somebody close to you wrote that.
I think so. Yeah.
Okay, one of the big picture ideas in here, and you gave us a very nice history of the relationship between math and physics, stretching back for centuries even, and that's a useful thing, a very useful thing that I've not read quite that way before, and that resonates so much with something that is a question that sooner or later comes to the mind, I think, of every physics student. Is what is the deal with math, and why does it work so well with physics?
Yeah.
And so I've got two quotations to share with you and with people to provoke a question. Happily, Dirac is the one who said, no, let's start with Wigner. His famous talk, which is someplace on my screen here, at New York University in 1961, called The Unreasonable Effectiveness of Mathematics in the Natural Science.
Yep.
And that sort of puts the question there that always is hovering around these things. And I was very interested in early on, you quoted Dirac as saying the universe is so constituted that mathematics is a useful tool in its description. And immediately I thought, here's the question I want to ask. Might it not be that mathematics is so constituted that it is a useful tool in the description of the universe? So the question is not really in there. It's a sort of essay question. It's like, let's dive in. Let's try to rephrase that question. Let's understand why it's even a question that physicists find themselves saying, what is the deal with mathematics and why does it always seem to work so well? Yeah. And then talk about some of those and why it leads you to the conclusions that you get in the book. This is just, big picture things here, but
well, it is. I tell you, you've got to right to the heart of it. I mean, it's a very, very deep topic. It's a simple question, but it's a deep question, and I think it was perhaps best put by Albert Einstein, less than half a mile from where I'm sitting now. He was writing to an old school friend, and he talked about the central miracle of science is the deep underlying order of the universe. There's no reason necessarily why the universe should be so ordered, and yet we human beings know that it is possible, just as you said, to underneath this incredible variety and chaos that we see all around us from on Earth right through to the most distant parts of our galaxy, right inside the atom, we could describe all this teeming complexity in terms of really basic, simple rules written in the laws of mathematics. Einstein described that as a miracle or as an eternal mystery. It's something that possibly we'll never be able to understand completely, but we do know that it works. And I mean, I think that that mystery should be stressed more. I mean, when you're talking to kids in the classroom, it's just as you said. It happened to me when I was at school. You do your experiments and what have you, and then the teacher starts writing down math. And what was never stressed to me is, well, hold on a minute, how come what you were learning in math classes works perfectly when you're describing the real world? Now, at present, we don't have a deep understanding of that, but for sure it works superbly.
Do you think there's any relation to all those late night graduate school discussions to the question of whether math is invented or discovered?
Well, yeah, you keep asking these deep questions. I might hand over to Joanne.
He's gonna leave, Jeff. You're scaring him.
I think, if you'll allow me a broad brush, I think most mathematicians think that they are discovering things when they, when they talk about discovering a theorem, like Fermat's last theorem or what have you, right? They think there's stuff out there, so to speak, that they can discover if they're smart enough. All right. In a very similar way, I think it's also true that physicists believe in their hearts that if they're smart enough and they work hard enough, there are laws, regularities in the universe that can be discovered. And yet, philosophers can make hay with this, because how can you prove that's the case? Right? And my view is, I'm not a professional philosopher. I don't think you can prove it. I mean, I was asking a friend of mine, Nima Arkani Hamed, just over the corridor, and I said, do you believe they were invented? He said, I'm a hardline Platonist. These things are out there. I am sure. I said, how can you be sure? He said, I feel it. Yeah, that's actually not very scientific, but I mean, that's what scientists do. They go to work every day, right? Because they believe there's stuff there they can discover.
You've gotten to sort of the central, acentral tension or friendly game between the mathηματicians and the physicists. Yeah, I don't want to overplay that for people.
No, you should.
We really might be fighting all the time.
Yeah,
but the mathematicians, as you just said, say, "Can you prove it?" And the physicists say, "Who cares? It works."
Yeah. Well, that's a different thing. It's very important, but it's that what you've highlighted there is the different cultures. Physics tends to be on they're not so worried about clarity of definition and about rigor. The pace of the subject tends to be very fast. They're very quick to discard things, often to follow bandwagons. Mathematicians work on a time scale of sometimes centuries. They're prepared to wait centuries to discover things. Right? I must come back to that game thing, because that game thing is important. And it's worth going back to the great theoretician Murray Gell-Mann, who died a few weeks ago. And he actually said, I saw this in one of his obituaries, that he's playing this game in physics, and how amazing it is that sometimes he finds that game applies to the world, to the universe. It was put best, I think, by the English physicist Paul Dirac. I think he put it beautifully when he said that mathematics is a game where the rules are invented by mathematicians. Physics is a game where nature gives us, it has its own rules, and we have to understand them. Now, what's incredible is that the rules the rules of the game that mathematicians find so interesting are just the ones that are so central to our understanding of the universe. That's a mystery. That's exactly as we were saying at the beginning.
So it's no surprise that physicists tend to like puzzles.
Yeah. Well, they both do. But it's also important to say that maths and physics aren't the same. That's very important to distinguish. Mathematicians could, in principle, work in darkened rooms, shut off from the rest of the universe, and they can work with their patterns. That's what they're fundamentally doing. They're working with patterns of thought. Physicists cannot do that. They are accounting for the universe they live in, for what they see, right? And so you've got these people who could be locked away, and the people whose essence is actually observing the universe. And the amazing thing is that they are working on common territory.
Yes, but when the physicists are doing their observations, and remember, I'm an experimentalist.
Yeah.
What are they looking for? They're looking for patterns.
Yeah, they are.
So you've got patterns for the physicists, you've got patterns for the mathematicians, and now the question is, why do they seem to match up sometimes? Well, we'll get back to that, and there's some other questions.
Sure.
They sort of come after we've laid a lot more groundwork.
Yeah, sure.
So I don't know. Do you want a historical picture? Does it? If I think of the mathematization of physics as starting sort of with Galileo, what would you say? Does that seem about right? Or
it is. I mean, I think that maybe I'm biased because you may have got from my accent. I'm not American. But you spotted, Joanne. Okay, very good. So observant. But I think that
you're going to say Newton, right?
I am. I think that's where the modern subject that we call theoretical physics, which is it's a horrible, intimidating phrase, but it basically means trying to discover and understand the laws of nature set out in mathematics. Now, in my opinion, the clearest, best place to start, which isn't to say it's just the only place that you can start, but is the publication by Newton in the 1680s, right, of his Principia Mathematica. That was a fantastic achievement, right? But he was standing on the shoulders of giants, as he said. He was working on, as you rightly say, building on Galileo, building on Kepler, right the way back to Euclid and Greek mathematicians. But what Newton did was absolutely remarkable, because he took this thing which was known about gravity and set up a whole scheme whereby this simple force, gravity, can explain the dropping of an apple from a tree, the orbit of the moon, the tides, the paths of satellites, and what have you. And he had a way of calculating motion under that force. Now, that was an unbelievable achievement. And he also, this is really important, because I bet you're going to come back to this later, he stressed that the way you do science is to set out these laws mathematically, which gives it generality and precision, but you must test those things against the most accurate experiments. That's absolutely central.
Yes, we will come back to it. You do, I do, everybody seems to. But Newton was a big philosophical shift too, of being able to describe things like this. The universality of laws, the whole idea that perhaps there is a big picture that is somehow simple and emergent from a small family of
laws. That's absolutely right. Really important.
A whole lot of things that came along with Newton's equation, right?
Yeah, that's right. Yeah, you've got it. And I have to say, because we mustn't entirely focus on Newton. I mean, Descartes was the person who really was responsible for this idea that we all know about, virtually everyone knows about now, the idea that there are universal laws of nature. People could talk about this now, right? It's a routine part of our understanding of the way things are. But it was Descartes who first really made that central, and Newton who really showed how powerful that could be.
Yeah. Then there's a lot of richness in between there. We're trying to get to the 20th century, so Joanne feels at home. But, it's like, so now we have Newton, and then stuff happens, and then we get field theory.
Yeah. Okay. Well, remember that Newton was pretty smart. I think we've agreed on that. But he knew that although that he had a great system for gravity, which is that he didn't finish I don't like using the genius word, but I mean, I think you could pretty well say that Newton was a genius. But even he didn't finish off all those calculations because things were just too difficult. He couldn't prove that the solar system was stable and what have you. But the one thing in retrospect that he certainly knew that he couldn't do was to describe electricity and magnetism.
Yes,
and we're all familiar with that, right? And it was a craze after in the century that which Newton died. You know all these phenomena that we see at science centers and what have you, of magnets and electric shocks, and with Joanne's hair there, you imagine her plugged into electrostatic thing. It would be an amazing sight, right? Right. But the problem is we have these phenomena, but we don't have basic laws to describe them. And the person who did that, I think it was against the odds, was the Scot, I'm afraid going back to Great Britain again, but James Clerk Maxwell. That was a surprise because at that time, this was in the 1850s, he did his fantastic work on this. But at the time, the really smart people in that subject of what we call natural philosophy, right, were Germans. Right, and that's where we were expecting the breakthroughs to come.
Not Scots.
Beg your pardon?
Certainly not Scots.
No. That's what I said. But it was James Clerk Maxwell got his mathematical education at Cambridge, and he saw in the work of Michael Faraday, who was working in London, that the key idea was the idea of the field. Now, everybody, even in at least I bet it's true in the States, it's certainly true in the UK, the idea of the field, the electric field, the magnetic field, we've got that, the idea of the iron filings around the magnet, right? Now, it was Faraday who really brought into the scene this idea of the field, that space around a magnet is not just nothing, but it's something that you can actually do stuff to. You can actually make active that space in such a way that it can affect iron filings. Now, most people thought that was a pretty far-fetched, possibly crazy notion, but it was Maxwell who thought that was the key to understanding it, and he was right. And that's what gave him the head start, that and his mathematics. And he was the person that set up these equations of theory of the interplay between between electricity, magnetism, and the ether.
Yeah.
That was an incredibly important theory in retrospect.
Well,
and actually, Jeff, if I could jump in, I just wanted to point out that actually the first half of your book is pretty much this older history.
Yeah.
And it really was so clear. This is the kind of clear writing that was also in the Strangest Man, the Paul Dirac book that I really appreciated. But, I just remember, of course, for myself, struggling with math in high school. But then by the time I reached college or university and I took physics class, and all the gravity and things like that, I think that was sort of background knowledge, like, you've got that, F equals ma, and here's this equation. Like, you sort of take those for granted. But when we got to electricity and magnetism and Maxwell's work, I was like, it really hit me how, wow, math really does explain the world. And I don't know why F equals ma did not do that for me, but suddenly it was Maxwell's work that I went, this is amazing. And then it made all the rest of physics easier for me.
Really?
To see how it, these things you could describe, why is, resolution not the same as magnification? Because the formulas are not using the same variables. It's not the same thing. So it was amazing. And I do have to say, Faraday is sort of one of my favorites. And I think that's because he was an experimentalist and wasn't so crazy about math either.
No, they say, I've heard really good Faraday scholars say that the most advanced mathematics Faraday did was balancing the books at the Royal Institution.
Yeah. Right? Really?
It was not, just as you say, Joanne, he was not a mathematician. But he had this deep feel for the bending of these magnetic field lines and electric field lines and how electricity and magnetism depend on each other. He had this incredible feel for these fields that he didn't invent, but he believed were the central part of nature. So,
but now, even as a biologist, you can't say anything unless you've got some numbers to back it up.
Good, I like that idea.
And so I guess Faraday was maybe the end of that, right? He's the last real person to be able to say, yeah, this is good and we can describe it, but now we need numbers, right?
I think that's a very important point. And in fact, let me just build on it and say that we have to remember that, that yes, in physics, what we're mainly talking about today, you look for a mathematical theory, right? In order to account for your experiments. But it's not always the case that you have a mathematical law. For example, look at Darwin's theory of evolution by natural. No equations in there. Plate tectonics, incredibly important theory. Show me the fundamental equations in there. I mean, you can do very good science, right, without that mathematical approach. Not everyone is going to be a great mathematician, right? But what we're saying here is that in order to do deep, to understand the deepest form, the deepest level, like Einstein did and the quantum mechanics people did, then you do have to use mathematics. But it's fair to say you don't have to do mathematics to do science.
That's true. That's true. Well, even E.O. Wilson has thoughts on this as well. And if you're not good at math, but you do need to find someone, because every modern paper in biology, geology requires some sort of mathematical weight.
I know. You need to have that's a really good point, because he really brought home to me. I loved his autobiography when he said that part of the skill of being a good scientist is knowing when you're out of your depth and getting someone to help you. So
yes, a little modesty goes a long way.
Yeah, it does. Yeah,
I think Joanne, that's really keen insight, and it's interesting that these days you hear about high energy physics and field theories and things, and it all sounds so esoteric, but we're talking about these iron filings on the magnets and things, and it's the same fields. This thing that permeates space and does stuff that you can see if you look at it the right way. People really do, I think, have a little more intuition than they give themselves credit for about that. Really, but one of the stories about Maxwell's equations that I always find really cool and gets us to the 20th century, I think, is that there was this constant that we now call c, and the discovery that c seemed to look an awful lot like the speed of light. And then the fact that maybe it is the speed of light. What a connection to make between c,
absolutely amazing,
Maxwell's equations, electricity, magnetism, and now it becomes electromagnetism, and we're that close to Einstein and relativity already. Conceptually.
Can I stress that is one of the great discoveries of the human race, in my opinion. Just like Newton discovering that the gravity that pulls your apple to the ground is the same as the one that holds the Earth in orbit around the sun and what have you. And with Maxwell, it's looking at these esoteric phenomena and actually saying light is electromagnetic. So suddenly, what was two subjects becomes one subject. That's an amazing thing to do. Right?
Well, this will help some people who are surprised when some scientists and historians say, well, we tend to think that Maxwell may have been one of the great, if not the greatest physicists of all time. An awful lot grew out of those.
It did. But let's what I suggest we do is move on to someone who probably would have agreed with you. That's Einstein. He said that Maxwell influenced him more than anyone. That was a quote I found quite late in the research in my book, The Universe Speaks in Numbers, that it was in 1926 he said that it was him Maxwell more than anybody else who influenced him. And it goes back to an earlier theme, that when Einstein went to college, this was in Zurich, he was pretty much convinced that to do physics, you only really needed to do what was, by his standards, basic math. Now, I don't just mean the multiplication tables, but I mean the sort of math that you would have done a century before. You didn't have to be a really hotshot mathematician. And he believed that was really an indulgence, something you just didn't have to bother with. And you've got to say that when you look at his great year, 1905, when he and his wife had a 1-year-old baby, and he wrote 3 absolute classic papers, in fact, a 4th one as well, right? He did that with really quite basic mathematics. He introduced special relativity, which is a new theory of new way of looking at space and time, modified from Newton, light quanta, the reality of atoms. It's really important to understand he didn't use fancy mathematics in that.
Can you give us a? I'm sorry, I've just been thinking, it's like his honoring Maxwell, and I've always enjoyed revealing to people who don't know it the title of his first paper about relativity, and we know it as relativity now. But give us the sentence about the connection between relativity and Maxwell and electricity and magnetism.
Well, yeah, that's quite subtle. It was called On the Electrodynamics of Moving Bodies, which is quite terrifying. We now call it, as you say, special relativity. I think it was Max Planck, an admirer of his, who first called it relativity. But Einstein was talking about how the equations that we described to Maxwell had what we call an invariance, the mathematical invariance that established a new link between space and time, and that did change our whole concept of that, right? And it's changing now, even in the present century. That was an amazing achievement deduced from Maxwell.
Right, and all of this comes from considerations about light and its apparent absolute magnitude, and also its interaction with matter to the electron. The electron is going to figure mightily when we get to Dirac too. Yes. Okay. Well, there we are. There's relativity. That's easy. Then there's that other relativity.
Yeah, but hold it though. Let's talk about when Einstein saw the light, so to speak. Yeah. Because when he turned his attention to gravity, he found that he couldn't make headway without using advanced mathematics.
Yeah,
that was a big surprise to him. It was around 1912, right? And he, with an old school friend of his, who's then head of the mathematics department when he was working, he showed him that you needed to use this branch of mathematics called differential geometry. Sounds terrifying, I know, right? But you needed to understand he applied this curvature of spaces to curvature of space-time, and it was using that insight that Einstein developed his theory of gravity, which made him a worldwide celebrity after experiments gave support to that theory.
Since you're there so close to his office, do you have some insights? How did they make that connection that differential geometry might be the thing? Who went closer to whose office?
Well, it's Sven Grossman. It was Einstein was floundering. I think it sounds like a strange thing to do. He didn't know how to proceed, and his friend Grossman said, "This is what you need." And this was we've used the word before. It seemed like a miracle. Einstein didn't know how to move forward into this new terrain, and there, sitting on the shelf, done by mathematicians some 30 years ago, was the perfect machinery he needed to complete that theory. So it looked like a miracle. It was just sitting there, and the mathematicians had done it. People like Gauss and Riemann, they'd done it decades before. And he took that machinery off the shelf, and his preeminent genius managed to use that mathematical framework to describe gravity. And it's really worth stressing here for people like almost all of us who struggle with math. Einstein really struggled. He described himself as a bewildered ox at one point, right? He had this mathematics, right? And he found it extremely difficult to relate it to things that apply to the real world. And there's a story here that I think really does, because it seared its way into Einstein's consciousness. Einstein, this is in the summer of 1915. So he'd been working on this, for almost 8 years. Right, and he somehow felt he was close to the final answer, the new law of gravity, and he did something that later he might have regretted, because he went down to Göttingen, which is one of the great capitals of mathematics and physics, and he talked about his incomplete theory to the mathematicians and no doubt some physicists, and they saw that and he told them that his theory wasn't finished, and in the front row of that audience was David Hilbert, who was one of the world's greatest mathematicians. And he saw, and they all knew, that Einstein was floundering. They knew he wasn't a great mathematician. And Hilbert saw the opportunity and started working on that theory. And to cut a long story short, Einstein beat Hilbert to that post by a matter of days. I mean, and Einstein always credited mathematics as helping him get his ball over the line, so to speak, right? And that's the thing that transformed Einstein's belief in mathematics. He really believed that mathematics was the lodestar, the thing you follow if you're trying to develop a new theory. That was an incredibly important event in Einstein's life.
there's a given what was going on at the time, and I think about quantum mechanics happening at the same time.
No, that was later. That was later.
Yeah, later, but
Yeah.
it was in the air in the early part of the 20th century with the quantum mechanics of having Schrödinger's equation, having Heisenberg's matrix mechanics, later Dirac's formulations. And I've always wondered, do you think that the formalism that Einstein used for the general theory is the only one he could have used?
Yes, I do. I do. I mean, well, he had no choice, but there will be patterns that are more subtle that might supersede it. But he definitely needed to go to differential geometry in order to get closer to that theory. I just want to wind back a little bit, because there's a danger of getting our chronology mixed here.
Mm-hmm.
In around 1925, as you say, the most revolutionary theory of the 20th century was discovered. That's quantum mechanics. Mm-hmm. The idea that the theory of motion on the atomic level is not like the theory of motion that Newton set out so brilliantly. You need a different approach, and that's called quantum mechanics. Yeah. That was a true revolution. It really did look like a clean break with what Newton had done. Now, as I say, that was an authentic revolution. It changed everything in physics. But Einstein, by that time, Einstein admired the theory, but he didn't trust it as being the last word. And at that time, he was getting interested in extending his theory of gravity to electricity and magnetism, and that's where he started to become semi-detached from his colleagues. Mm-hmm. He wanted to extend his theory of gravity to electricity and magnetism, but almost everybody else, crudely speaking, was getting behind this new theory of quantum mechanics, and that's where Einstein separated from his peers.
But now you've introduced the two players that show up later as I think it's an important notion when you talk about how, well, theorists try some new mathematics, but they know that they have to be consistent with quantum mechanics and special relativity. So why those two?
Yeah. Well, those are two foundational theories, right? Special relativity is about the correct description of motion, right? For bodies moving uniformly. Quantum mechanics is a theory of matter on the smallest scale, and we know that those theories, let's just jump to the present now, no measurement has ever been made that's contradicted those theories. That's really, really important, right? And that's why the greatest physicists now, if they're doing an ambitious theory, they know that they have that whatever theory they come up with has got to be consistent with relativity and quantum mechanics. That's an incredibly important pair of guide rails.
And then a couple of ideas that I tend to associate with special relativity is that you need as foundational is the idea of space-time.
Yeah.
And then the idea of invariance, which starts to bubble up as a really as a handhold.
Yep.
Almost.
Yeah.
So say a little bit about those, and then we've got all these pieces lying around to get us to the argument of the book, I think.
Mm-hmm, mm-hmm, mm-hmm. Well, I mean, I don't want to go too deep, because otherwise, Joanne will chide me. But she'd be right. But you'll know that we know now that Newton's idea that there is a unique, all-pervasive sense of time throughout the universe, that measurement is something that we can all make independently, that was superseded by this idea that space and time are very closely interlinked, and that your version of space and time is not identical to my version of space and time if we're moving relative to each other, and that was extended by general relativity. So that was very, very radical. And I say again, that simple reinterpretation of space and time has never been questioned experimentally. And quantum mechanics too, that was the first theory, as far as I know anyway, that appeared in publications where people actually had the mathematics, but they didn't know how to interpret it. And it's still a matter. today of controversy. I'm sure you've discussed this before. But the thing is that with a basic interpretation, it has never been found wanting. Yeah. So you bring those two things together, and as I say in my book, you get magic. You get magic in terms of new mathematics, and you get magic in terms of a new description of the universe. So those two things are incredibly important.
But the slipperiness of relativity isn't entirely slippery, because there is something that's invariant in there. And the speed of light sort of fixes us with a little bit. So that not everything, people love to say everything's relative. It's like everything, well, except something. And there's a little something to hold on to that
no, that's right. That invariant thing is right. Remember how extraordinary that seemed at the time, that no matter what state of motion you get, for observers that are moving uniformly with respect to each other, they all measure the speed of light to be the same. And this is completely counterintuitive. You think if you're moving faster than I am, you would measure speed of light differently to me, but no, Einstein said they're the same. That's what makes these calculations so counterintuitive to most people.
And then it turns out that, we can just say this maybe, but that the invariance, this is one of those miracles in physics to me, the invariance is intimately related to conservation laws, and they keep showing up.
Yep, that's right. Yep, that's quite Naomi Noether did. That was one of her great discovery in physics, a great mathematician. Yeah. Okay.
Yeah, I'm resting.
We better check in that Gell-Mann's still following us, and if she's not.
No, I am, and I felt like you explained this all really well in the book, and just as you said, magic. There were things in the book where people were like, I'm amazed, I'm enthralled, I am I don't even know how to describe it. It's just like the fact that physicists were even surprised at how well this was working.
Yes.
And of course that mathematicians were a little maybe insulted that the physicists were doing this okay.
That's right.
Was a surprise to me.
That's absolutely right. And that's something we haven't stressed enough, I think, that by finding what is a favorite term in Göttingen, which we described before when Einstein went there, is it's a lovely phrase that you could trace back to Leibniz, actually, and that is this pre-established harmony between math and physics. Now, this means, right, in modern parlance, and it's and in the last few decades, this has really come to the fore, that, and you mentioned this, Jeff, earlier as well, not only is math essential for developing our understanding of physics, in other words, our understanding of the universe, but our understanding of the universe feeds back into mathematics. Yeah. So you have two sets of unreasonableness. You have the unreasonable effectiveness of math in physics and the unreasonable effectiveness of physics in math. Again, show me an explanation of that. I don't give one in the book because nobody's ever given me one, no matter how eminent. Edward Whitton along the corridor here, the greatest mathematical physicist of the last 50 years, without doubt. Whenever I ask him about this, he says the equivalent of "search me," but he knows it's true. But the explanation of it is a different matter.
Right. So that's interesting. But let's get to work.
Yeah. So you mentioned Whitton, and I had spoke to you before we went on air about something that struck me in the book. Was Whitton at one point was really like, why can't you guys, we can teach, first year graduate students about this physics. Why can't you mathematicians get it? And then he changed his tune. Do you want to tell about that?
Yeah. Well, it's funny. In writing my book, I spoke to a lot of leading mathematicians and physicists, and incidentally, virtually every one of them checked my account in the book to make sure it was accurate. And one of them, Dave Morrison, who's a very, very good mathematician in Santa Barbara, who came to see me one afternoon. I was a resident there, and he said that he remembers Edward Whitton organizing a summer school where mathematicians were trying to learn the type of field theory you use to understand interactions at the heart of atoms. And this was stuff that physicists just learned very easily, right? Yeah. And these mathematicians were really, really struggling. And very, very unusually, Edward lost his cool for a few seconds and says, how come you brilliant mathematicians can't get this subject that we teach our students routinely? Anyway, I sent my account to Edward, and I knew it was true because Dave said he remembered it very, very vividly, and a couple of students were there. And Edward said, oh dear, okay, if I did say that, I'm sorry, because I now realize that this is not a, mathematicians have to jump in with no preparation and start doing advanced physics.
Yeah.
Right. So this is why it's tough for mathematicians to import these ideas, because they don't have the background that the scientists have. Right. Just like for a regular physicist, it's very, very hard work to do advanced mathematics, because you're having to jump over dozens of courses that mathematicians do in their training. It's very hard to move outside your comfort zone.
Mm-hmm. Right. So is there hope? There's, I guess the only hope for people like me, who's a biologist, is for people like you, Graham, to write books about this, to make us aware, to make it more digestible, right?
Yeah, yeah. Well, I try to. It is a remarkable coming together, though, of those two subjects. I wonder if that might ever happen in biology. Actually, it's a genuine question about whether biology might one day be led mathematically. I don't know, right?
Yeah, we use a lot of stats for sure.
Yeah, for sure.
But
and there are great population. I met John Maynard Keynes, right? With my book, It Must Be Beautiful, which is about the great equation of 20. And I loved him. I thought he was brilliant, incidentally. And he was a really gifted person mathematically. He wouldn't consider himself a mathematician, but he loved to play with the mathematics of evolution, right? And again, I thought this guy was so smart. Right, and he was, no doubt about it. He's now passed, but I don't think he would ever say that mathematics showed him the way ahead. Rather, it was a great tool to understand the complexities of evolution that wouldn't otherwise be obvious or plain.
Right, yeah, and to give it a way to be explained.
Yeah, and he had a brilliant intuition for. He was one of the great mathematical biologists.
And that's a good example of math in and anything with populations.
Yep. Yeah. Well, of course, actually in that book, Robert May, there's something called the Logistic Map, which looks at the populations of isolated communities of, fish and what have you, how they can become chaotic, right? They can change in completely unpredictable ways, and how you can understand that mathematically. That figures in Tom Stoppard's play Arcadia, brilliantly handled by Tom Stoppard. So mathematics has got things to teach biologists as well.
It's true.
What I'm interested in is whether it could become something that could show biologists the way ahead.
Interesting. That's an interesting thought. I've not seen any indication yet.
Me neither, but you never know. Centuries time, your great grandchildren will look back and think, how crude is this conversation?
That remark gets us almost to what you said at the beginning of the book. Is one of the central contentions of the book is about who does the leading and who does the showing. And we talked earlier this year to Sabina Hassenfelder.
Oh yeah.
Yeah. And you mentioned her like on page 6, and I thought, and Joanne knows this. Yeah. I said, oh dear, is he going to be one of those, anti-Sabina people? Or are we going to have things to argue about? And you've put all this together and got to the end, and I finally told Joanne, I said, no, I think they agree. And I'm not sure that you see it that way, which is fine, because that gave you a lot of scope to present all these ideas and all their connections. But in the end, when you say something like, so here are people nowadays, you're doing math and they're using math and they're extrapolating from that, and they don't have anything that can be seen yet by physics experiments, but we'll probably get to there sometime. You say, yet these were not unconstrained exercises in pure thought.
That's right.
Theorists knew that every new idea had to be consistent with quantum mechanics and with the special theory of relativity.
Yep.
And so that leaves you in the place of saying, and I'm happy to follow you there, why not use the math to see where it takes you? And every now and then you see where you've gotten to and whether it makes sense to be there.
Yes.
But there's no problem with extrapolating. It's just that we know extrapolation can sometimes lead you astray after a while. But I felt like the two of you came together from maybe slightly different viewpoints.
Yeah, I mean, I don't. Very broadly speaking, I think that Sabine has a point, but I think I personally think I respectfully think she exaggerates it. I don't think the community as a whole is lost. I simply don't think that is true. I do think, nonetheless, she has a point that there is a great danger of that happening. I mean, once we end up with physicists who just don't even look at observations, right, who are completely entranced by mathematics, we're in serious trouble. I simply do not think that is true. I mean, I'm sitting in an atypical address here, but Nima Arkhami, Hamed across the corridor, Edward Witten, Juan Maldacena, these people are very close to experiment. Right? They really are. They go to it, so they are much, of course, they're a million times.
They're working within these constraints, even if you don't always see it.
They are, and they're not lost. They know there are problems. That's a different matter, right? Yeah. But we're doing something here. The very, very big picture, of course, is that we're doing something incredibly ambitious. We're taking our understanding of gravity, which Einstein gave us, so beautifully in 1915, and they're trying to unify that with our understanding of the forces responsible for holding together atoms. So very big gravity, very small. They're described by different mathematics, superficially anyway, and it's an incredibly big ask to bring those two things together. And it's really, we still haven't done it. That's true. We haven't finished that. It's an incredibly challenging thing to do. Now, the best candidate we have for that is something called string theory, where instead of thinking of all the fundamental entities of nature being tiny particles, rather that you could think of the particles that we see in the particle accelerators as vibrations of a tiny, tiny string. So the elementary thing is the string, not particles. And there are more advanced versions of that, which we don't need to go into. Now, the criticism of string theory that I think I'm right in saying that Sabine would make, and many other people make as well, is that it hasn't made any characteristic new predictions that experiments can test and have tested. That's true. That's true. There's no doubt about that, and it would be foolish to deny that. The thing is, though, that doesn't make the theory wrong, right? Yeah. They also another big criticism is that the ground state, the simplest states of those theories, there's not just one basic universe. There are zillions upon zillions of them. So which one corresponds to reality? That's also a fair point. Doesn't mean the theory is wrong. It means that we have more things to understand. So that's why I say that it is fair. There are very distinguished physicists like Steve Weinberg, whom Sabine interviewed in her book, entertainingly, and he said he's found it disappointing that the string framework hasn't made direct, and that's a perfectly fair point. Where I respectfully depart is in thinking that this means that we're lost in some way. I simply don't accept that. Right? It's a free country. It's a view, but I will say one thing, that is not the majority view. It really isn't among physicists.
I'm laughing because you're saying it's a free country, which is usually for America, and we've got Sabine and we've got you, so Sabine from Germany.
Well, you've got to respect
everyone just comes to America and says it's free here.
Well, but it is important. Look, science has got to have critics. They've got to be well informed. They've got to be, they've got to, but that said, I think it's accurate to say that the notion in physics, right, that the whole, that they're following this thing with this string framework and quantum field theory, that they're lost and that there's not a huge amount to commend these things. I personally think is misleading, and I think it's a minority view. That said, I will say one thing just to undercut my own argument, because we're friends. I love George Bernard Shaw's statement, right? The minority is sometimes right, the majority is always wrong. I love that, and it's I would say it with my tongue in my cheek.
Yes.
But I think I'm very confident that the way that leading the world's top, not just them, but the physics community is not on a path to nowhere. But there's no doubt we're in a challenging time now without experiments. That's undoubtedly true.
Right.
I'm happy to see those extrapolations go on. I think personally, my view is I'm usually happier when there are multiple paths being extrapolated, because you never know what's going to pay off. And
no, you don't. You never know what's around the corner. That's absolutely right.
Right. So speaking of things you don't know what's around the corner, but yet you made some predictions of 6 things that you think will remain.
Oh, I knew you'd point the finger at me like that. How cruel! How cruel!
Well, it's right here.
Never make predictions, especially about the future. Yes, I know.
Or 6 ideas you expect to stand the test of time.
Yeah. Okay. Well, don't let me detain you by putting all of them down there. But let me say there are right. Let me just do 2 of them. Right. That one of the triumphs of quantum mechanics in the hands of Paul Dirac was that the magnetic monopoles may emerge naturally from quantum theory. Now, what does that mean? Well, everyone learns at school, right, that every time you see a north pole, there's a south pole pretty close by, right? They come in pairs, north and south. Now, Dirac, it had been argued by other people in quantum mechanics, it really is possible within that formalism just to have an isolated north pole or an isolated south pole, right? Now, in modern theories, what we call in theories that combine relativity and quantum mechanics, in what we call relativistic quantum field theory, sorry about the name, these things must exist. The universe should be teeming with them, right? Nobody has found them. Right now, I predict it's not in any way unique to me that those magnetic poles will be discovered one day. Right now, it's a hostage to fortune, but they are now as real to physicists, those things, as the moon was to Galileo, for example. Right, but it is absolutely true to say there has been no confirmed prediction of those things. I believe that there's so much evidence within the theory that they exist that they will be found. Perhaps a bolder prediction. Again, I want to stress this is not just me talking. I mean, what matters is the community, right? But one of the perhaps the best tested theory we have, which is the quantum field theory of the basic forces of the atom, tested to umpteen decimal places, right? Which amazing predictive achievement. There's something very strange going on there. Very, very strange, because when you use those theories to calculate subatomic interactions, you often, and I mean often, do calculations that are hundreds of pages long, and they distill down to something you can write on the end of your thumb, one line. Right? This isn't just something that happens occasionally. This happens a lot.
Yeah.
Now, that is a cartoon, but what I've just said is true, but that is what leads many theoreticians to believe that we're missing something in our framing of that theory, that if we look at it in a different way, right, perhaps with a new vision of space and time, that theory will be a lot more compact, a lot easier to discuss. So instead of Joanne looking terrified when I say quantum, right, that it may be possible to cast it in a way that Joanne can say, oh, good, I can just write this down on one side of paper.
Right. Well, and weren't there a group of researchers who were trying to simplify the Maxwell equations to make it even more compact, right?
Well, you can.
Yeah. And that was something that struck me in the book too. So, you know what? I'd like to ask you a little bit. You've been writing for a long time.
Yeah.
You're a very diverse person. So, what would you say to someone who wants to write about science? What would you recommend?
Love it first, just as you do, and Jeff does. That's really important. And again, I'm not being original here. Richard Dawkins, I remember reading an article by Richard Dawkins when he said, never try and write about something, you know, at length, so to speak, unless you really love what you're writing about. And both of you two have a love for your subject that shines through. to write something just for the sake of earning a buck, to me, is a hiding to nothing. Yeah. But if you've got that enthusiasm, it will drive you through the difficulties of understanding and will release those creative energies. But you've also, of course, if you're a writer in the game that we're in, you've got to try and find ways, a courteous introduction to people who don't know about it. They're not fools, they're not idiots, they just don't know about the subject, and they need an entertaining and an informative and accurate way into those subjects. And that, to me, is the fun of it, that tension between stuff that you find difficult but challenging, but you love it, and the wish that other people can share in your enjoyment.
That's really good advice. And Jeff and I both commented separately outside of our program here that there were some difficult new things in this book, but we see it actually as an introduction, like we're going to start encountering this information more and more. And for that, I actually thank you, because maybe the first time around I won't understand it, but the next time I see it somewhere, I will go, I remember Graham talked about this.
We come across stuff, and the first time you look at it, you say, I'll never understand that, right? You come back a second time, and then you read another account, you go back to it, and gradually it falls into place, right? And I personally, but in my own personal view, is that I think we need more books that don't just go over very familiar territory, but actually take us to new things. Right? And they are more challenging that way. That is true. But I think we need that for the health of the field.
No, I mean, and I was thinking of that. And when Jeff first made this comment about, well, it was a bit tough there. It was new. And I went, yes, it was. But I remember feeling grateful. And I think you're right. We do need to do that. We can't just always have a nice, soft, non-challenging, review of things.
Help the non-specialist reader find the way to tell the story. It's hard to tell them the first time, but I do tell people sometimes, like, this is physics, this is science or math, and some of these ideas are not for fast reading. No. Some of them take a while to assimilate and digest. Don't worry about it. Read them slowly, and then that's what Joanne and I were talking about. It's like, here are new ideas, and you'll see them again, and you start getting the layers, the meaning, and it grows. Don't worry too much at the beginning. If you don't understand it, don't say, I don't understand science.
Really good advice. Can I add a couple of links to two Oxford friends of mine on this? First of all, Joanne, you talked about your being a biologist. What I know about biology, you could stuff in a thimble, right? But what I learned actually, the thing that really blew me away was the book by Richard Dawkins, The Blind Watchmaker. Right? And that, it wasn't just the content of that, it was the grace of it. It was the vastness of the ideas, the eloquence, the humor, right? And that made me realize that, there's a big world out there of biology and living things that I need to understand. The other one, picking up on your point, Jeff, is the great Oxford mathematical physicist, Roger Penrose, who is the most urbane, he's the most lovely man, right? And his books look very technical. He said, look, if you come across an equation, just your eyes, just go past it, go back to it on the second, third reading, right? In other words, don't let it intimidate you, because there are things to be gained from, as you say, just taking a relaxed attitude to things.
Just seeing it. Yeah. Excellent advice. Thank you.
Well, both of those people, I think, gave excellent advice.
So yeah, and I think you answered a question I was going to ask, like, who would you recommend for people to read? So, and I'm just sitting here, thumbing through Strangest Man. And because actually I remember there weren't too many pictures in here, but it is a focus book. But your book actually has pictures and it has equations and stuff like that. So actually I feel, it was funny, even in the middle of feeling maybe a little overwhelmed by some of the information, like seeing a picture of the person who does the science was a little grounding and calming.
No, that's right. And I think that for me, certainly in physics, you've got to have a human dimension I mean, you know, in biology, you've got the furry animals, you've got the whole vastness of life. But
You
in
care
physics,
about life.
if you just talk about something, a differential homomorphism or something, oh my goodness, what's that? You know, you've got to actually give it some flesh and blood, in my opinion. But you know, maybe in future generations that won't be necessary. But for now, I think we do need.
Yeah, no, and I even, like I said, I thank you for that too.
Sure.
So I thank you for the new introduction of material that I thought I'm going to see this again for sure. So that's wonderful. And then just including the human touch in there. And then of course you were talking about grace and eloquence. And those are words, you know, you use that for Dawkins, but those are words I was going to use for your writing. And I appreciate that.
Very, very sweet of you. I do appreciate that.
So is there anything else you would like to add before we sign off? No,
I'd just like to thank you for your time. I really great questions, and your interviewees are lucky people to have two such such people who love their subject so much and are so eager to share it with other people. That is something we need far more of that. So thank you so much.
You're welcome. We are glad you could join us. So,
my pleasure.
Jeff, anything else?
No, there's so much more. It would take hours, but I think there's the book, and people should read it and enjoy it.
Thank you, and thank you. We really appreciate both, and look forward to speaking to you again in another 5 years' time when I do.
Excellent.
Popped in late. This is we're talking to Graham Farmelo about his latest book, The Universe Speaks in Numbers. So, which was a great book to read. I'm really glad I read it. And Graham, hopefully we'll speak again soon. And thank you everybody for joining us.
Thank you so much. Take care.
Bye. Bye, Jeff.
Bye.
Bye all.